Alright guys, 5.6 studies the rational zero theorem, and the goal of this is so that you guys can go ahead and find zeros of a polynomial function, very similar to what we've been working on so far. Rational zeros, when we're talking about rational numbers, it's any number that can be written as a fraction, right? So go back to think about your study of rational numbers and irrational numbers. When we talk about number sets, whole numbers, integers, so on and so forth. Rational numbers are just numbers that can be written as fractions, that's all. So what the rational zero theorem states is that anytime you have it written like that, x to the n plus blah, 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 plus a, and all of the numbers, all of your coefficients are integers, so no fraction coefficients, then every rational zero, every single zero of that polynomial follows the same form. And the form is going to be really focused on the leading coefficient and the constant term. You guys got to memorize this idea of P over Q. It's going to be very, very important for what we're doing. P is going to stand for something really specific. It stands for the factors of your constant term. So any factors of whatever that constant term is. So if the constant term is 9, your factors would be 1, 3, and 9. Right? And Q is going to be factors of the leading coefficient. So if I gave you guys a leading coefficient of, let's say, 4, the factors would be 2, 4, and also 1. So again, P over Q, constant term over coefficient. I don't know why we use P and Q, to be quite honest, but those are just kind of the ones that are common in math. So here's an example. We want to list the possible rational zeros of the functions using that theorem. Now in this one, we're not given any x equals this, or here's a factor. We're not given any of that stuff, so that's when this comes in handy. So we're going to go ahead and list off our P and our Q. If it just says list the possible zeros, that's all we got to do. We don't have to do much with it. We're going to look at our P value. Our constant is 12. So our factors are plus minus 1, plus minus 2, right? Positive 2 or negative 2 could factor into it. Plus minus 3, 4, 6, and 12. Again, it could be a positive one we could divide. It could be a negative one we could divide. We have to test both positive and negatives, so those are really important for us in this. Our Q is a 1, so the only factors of 1 are positive 1 and negative 1. Now, if we want to list off what they actually are, we have to do P divided by Q. So we take every one of our P terms and divide it by every one of our Q terms. In this case, it's only 1, so it's kind of nice. So you have 1 over 1. It's going to be plus or minus. And then we'll be left with 2 over 1, 3 over 1, so on and so forth. Now, something to kind of keep in mind here when you're doing these, you'll have repeat values, like we'll see in the next example, and we'll kind of eliminate some of them. But in these particular cases, when our Q is 1, we're not going to leave them like that. We're going to simplify all those numbers, right? 1 over 1 really turns into just 1. 2 over 1 turns into just 2. 3 over 1 is 3, so on and so forth. But again, really, really paying attention to the fact that we could have positive 1 or negative 1 as a 0. And that's really what we've got to kind of keep in mind when we're doing this. Okay, so that would be us listing off, that would be our answer for listing off the possible rational zeros using that theorem. We took each one of our factors P and divided it by each one of our factors Q. Rather than writing out 1, comma, negative 1, 2, comma, negative 2, we could just indicate it using the plus minus. Let's take a look at our next example here. 4x to the 4th minus x cubed minus 3x squared plus 9x minus 10. All that inside stuff doesn't really matter. We're just looking at P, which is negative 10, and Q, which is 4. So our factors of 10. We've got 1, 2, we've got 5, and also 10. We're going to list off our factors of Q, which is 4. So we've got 1, 2, and 4. Now you're going to have quite a few extra little zeros in this sometimes. And some of these problems could get pretty lengthy. So keep that in mind. So if we want P over Q, we could have 1 over 1, 1 over 2. You could have also 1 over 4, right? Because that 1 could be over any one of those Q values. Similar to that, we move on to 2, and we're going to have 2 over 1, 2 over 2, and 2 over 4. Now, if you recognize it right away, you might not have to write that 2 over 2, because if we see 1 over 1 and 2 over 2, they really represent the same number. Same thing with 1/2, and then what we're also going to write, which our next one is 2/4. So if you guys are doing these and you recognize that early, you might not have to list them all off. Go on to our 5, we got 5 over 1, got 5 over 2, and also 5 over 4. And finally, our 10, 10 over 1, 10 over 2, and 10 over 4. Now, after you've gone ahead and you've done that and you got your 10 over 4, you're going to want to go back and you're going to want to simplify every single one of those fractions. And if you have any duplicates, for instance, if we get 10 over 2, that really equals 5. Well, 5 over 1 also equals 5, so you'd only have to list it off one time. Alright, so now let's go ahead and try to use these. We want to find all the zeros, and in this case the coefficient is going to be 1. So if we're finding all of the zeros, we actually want to know like x equals what. We're going to use that theorem to help us out. In this problem, x cubed minus 8x squared plus 11x plus 20, we're not given a factor already, right? We did that in the last unit. If I said x plus 6 is one of your factors, well, we did some long division or synthetic division and try to make the problem a little easier for us. We also gave you guys one's last lesson that I gave you a 0. I said one of your zeros is 3, which meant one of your factors was x minus 3. Well, I'm not giving you that this time. You're really not given anything. You're given nothing and just said find the zero. So we need a strategy to come up with. You guys could try to do factor by grouping because it's 4 terms, but if you took an x squared out of the first term, you're left with x minus 8. You can't take anything out of the second set, so you're 11x plus 20. Now those factors wouldn't match, so grouping's out of the question. That's when this P over Q idea really comes in play. So we're going to list off all of our values of P and Q and test them to see if we have any rational zeros. All right, P is 20, so we've got plus or minus 1, 2, 4, we've got 5, 10, and 20. Now, if you're kind of thinking ahead, you might be thinking, wow, this might take a really long time. And you're right. Some of these problems do. All right. P over Q is going to leave us then with 1 over 1, 2 over 1, 4 over 1, so on and so forth. So we're just going to write it out as plus or minus. Let's not even write that out. Ready? We'll just go with 1, 2, 4, 5, 10, and 20. Just reducing our fractions right away. Now those numbers, those P over Q possible answers, those are the ones that I'm going to test to see if they are in fact zeros of that function. And if it's a 0, that means it should be a factor, right? So we're going to test the values into it. Before we do that, there's a huge, huge, huge key idea that you guys have to kind of make a big conceptual leap for here. If something is a 0, right? If you said, hey, I found one, it's x equals 5. Well, something that's a solution or something that's a 0 means then that the factor it came from goes evenly into our original problem, right? The factor that it comes from is going to divide evenly into that original piece. In other words, right, if something goes evenly into it, it has no remainder. And that's super crucial here, is that if you guys test a point, right, we do not want it to have a remainder. We don't want to test one of these and get a remainder because that's going to indicate that it's not an actual solution. So we'll try some of them. Always try to start with the small ones. We'll test positive 1. We're going to test it using synthetic. And we're going to plug it in. So we drop the 1 down, multiply it, and we're left with -7. Multiply that, we're left with not positive 3, sorry, positive 4. Multiply that, we're left with 4, and a remainder of 24. That remainder is no good. What that means is 1 is not an actual solution. So we go on to the next one, test negative 1. Test it in. Let's do synthetic again. All right, multiply back in. Combine, we're left with negative 9. Multiply that, we got positive 9, so we're left with 20. Multiply, we got negative 20. And we don't have a remainder, which is a great thing. Which means x is negative 1 is a solution. Right, so negative 1 is one of your zeros. Now negative 1 really came from x plus 1, which means x plus 1 is one of your factors of that. Our goal then should be to find the other factors, right? Well, you guys just found them. It's right there. The 1, the negative 9, and the 20 really leaves us with x squared minus 9x plus 20. We always want to factor these things, right? We always want to try to take our big polynomials into smaller terms because then it's easier to solve. If I told you that x plus 1 is a factor, well then we can solve it and x equals negative 1. X squared minus 9x plus 20 is another factor, and we want to break it down. This one's a trinomial, so we could try AC method on it, right? We already got one of our zeros. Let's find the other ones. It's going to be x minus 4 and x minus 5 is what it factors into. And like I said, we wanted that whole thing to equal 0. So we set the factors equal to 0. And we're left with x equals positive 4 and also positive 5. So our answers for that whole thing are x equals negative 1, positive 4, and positive 5. Now this next example we're going to do is very long. All right, take your time with it. It's kind of tricky. It's one of the ones when the coefficient's not 1. Okay, so we got 10x to the 4th minus 11x cubed, blah, 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 plus 12. And the 12 is really important. Right, the 10, the leading coefficient, and the 12, the constant, are the two key important factors here. Our p is 12, so we've got 1, 2, 3, 4, 6, and 12, which is a lot of numbers to test. Especially seeing as q, 10, has a handful of itself, 1, 2, 5, and 10. Now, think about that for a second. You're going to do 1 over 1, 2 over 1, 3 over 1, 4 over 1, 6 over 1, 12 over 1. And then you're going to do 1 over 2, 2 over 2, 3 over 2, 4 over 2, so on and so forth. You're going to have a lot of possible numbers. Rather than sitting here and writing out every single one of these, of our possible p over q's, we'll just write out a couple of them. And we'll simplify it as we write it, right? 1 over 1 is really 1. You've got 1 half. We've got 1/5 we'll chest. We got 1/10 we'll go with. 2 over 1 is really just 2. You've got 2 over 2, but I'm not going to, I don't know why the keyword popped up, sorry guys. So we tested, we got one of our possible zeros as 1 over 1, 1 over 2, 1 over, we put the 1, right? Now our next p is 2, so we do 2 over 1, which is just 2. 2 over 2, simplified is 1, so I don't need to rewrite it. We got 2 over 5. We need to write that one. We don't have that yet. 2 over 10. 2 over 10 really reduces, though, right? If you reduce 2 over 10, you really get 1/5. So again, I'm not going to rewrite that one. Let's go on to our 3. So we got 3 over 1, 3 over 2, 3 over 5, 3 over 10. Let's hold off from there, right? That's enough zeros to test right now. Now, granted, we might not find one, which kind of stinks, because then we'd have to go to 4 and 6 and 12. But hopefully one of these works. Now, you guys got to be smart about what you test, right? You guys have these handy little things that looks like this. And I know my drawing, you already know exactly what it is, right? Probably not. It's your calculator. We're going to be really strategic about what values we actually test to plug in. Now what you're going to do is you're going to actually go to your y equals, and you're going to enter in that function, right? 10x to the 4th minus 11x cubed, exactly how you see it. And you're going to graph it. And on our graph, we're going to really pay attention to the values. And it's a curve that kind of looks like this here. You guys should actually take your graphing calculator and try this so you know what I'm talking about. And really looking at the values here, we're looking at zeros. Zeros are where it crosses the x-axis. So I can see 1, 2, 3, 4 of them, right? Now from there, I'm going to go ahead and list off ones that I think are pretty close to those 4 values. So that value all the way to the left kind of looks like it's in between -1 and -2. So I'm going to test -1/2. I'm sorry, -1 and -2. So that's going to be about -1.5. So I'll test -3/2, which is really 1.5, right? That next value kind of looks in between -1 and 0. So I'll test -1/2. Next one looks like it's really close to 1. Not quite there, but it's pretty close. So maybe 3/5. I don't know. I'm just kind of taking a guess on some of these too, by the way. But I'm taking strategic guesses, right? It's not just totally out of nowhere. They're guesses that are kind of coming from someplace. And that last one is like 2 point something. None of the fractions that I have up there right now really represent 2 point something. So I'm probably going to have to go a little higher with my P and my Q. If I keep going, let's go with, I don't know, let's go 12/5. 12/5 will give us a little bit over 2, so that might be close. All right, we could get really lucky, and we could have just maybe took a complete random guess and found every single one of them. Or we might have gotten really unlucky, and then none of those zeros work, and we got to try a whole bunch of new ones. Let's go ahead and find out. So we're going to use synthetic, and the synthetic can get a little weird because we're dealing with fractions, but it's perfectly fine. All right. We're going to list off all our values: 10, -11, -42, 7, and 12. We're going to plug in -3/2. Drop the 10 down, multiply -3/2 times 10, which will give you -30/2, which reduces to -15. Combine those, we have -26. Multiply, use your calculators to multiply, it's easier. And we have +39. Combine, we're left with -3. Multiply, +9/2. If you add 7 and 9/2, you get 23/2. Multiply, and we have -69/4 combined, and shoot, we are left with a remainder, which means that is not one of our numbers that is good. That's not a 0. So let's go on to the next one. Now, before we go on to the next one, that doesn't mean that that point that we found all the way on the left doesn't exist, because it does exist. All that it means is that -3/2 was not the point. It's somewhere over there, right? Maybe it's 6/5. Maybe it's, I don't know, 12/10. It's over there, but we just don't know what that value is. We took a wrong guess. So let's try to go for our next one that we picked, -1/2. Same deal. We're going to do synthetic with it. Hopefully it works. So let's plug it in. We'll drop the 10 down, multiply. We got 10, -11, -42, 7, and 12. I really hope this one works. Multiply those, we get -5. Combine, -16. Multiply those, we're left with +8. Combine for 34. Multiply those, and we have a +17. Combine for 24, and when we remultiply, we get -12, which is no remainder, which is great. Thank goodness. Right? We have a 0 now. One of our zeros is x equals -1/2. So I'm going to kind of scroll down a little bit and go on to our next piece, because we are far, far, far from being done for this problem. So we got x equals -1/2, right? And that 10, -16, -34, 24 is really our next component to it. So our original problem was 10x to the 4th minus 11x cubed minus 42x squared plus 7x plus 12. And we said negative a half works. Well, the factor it came from then is x plus a half. If you plugged in negative a half, so x plus 1/2. If that's a factor, your 10, negative 16, negative 34, 24, which we have from the synthetic part, is what the other factor is going to be. With 10x cubed minus 16x squared minus 34x plus 24. And it leaves us with a little something easier to try to work with. So now we focus on that second term, that second piece, and we try to factor it and break that one down. There's a GCF we could take out. Right? We could take a 2 out of everything, so let's go ahead and do that. If we take a 2 out of it all, we are left with, there's nothing we can take out more than that, so let's go with a 2. We're left with 5x cubed minus 8x squared minus 17x plus 12. Okay. And what I'm going to do here, don't get too confused. Hopefully you guys understand so far where everything came from. I'm going to take those first two terms and combine them into one, because typically we don't see x plus a half as an actual factor. So what you guys might notice here is that if I multiply the 2 into it, right, we'll be left with 2x plus 1, which looks a little more like the factors we're used to seeing. So I didn't change anything of the problem. I didn't it's not a new problem at all. It's just multiplying that 2 in to get rid of the fraction. And we still have 5x cubed minus 8x squared minus 17x plus 12. And we got to work with that now. Now, we're going to try to factor that, but unfortunately, grouping doesn't work, so we have to go to something else, which means that we're going to go back to that p and q. We're going to keep that 2x plus 1 off to the side. Do not lose it. A lot of people will. You guys got to keep in mind of it. All right, so p over q with this one. Our p is 12, and our q is 5. So I'm just going to go ahead and jump straight in to writing out all of our possible p over q values. Do plus or minus 1, 2, 3, 4, 6, 12, 1/5, 2/5, 3/5, 4/5, 5/5, 6/5, 12/5, and those all come from p over q for that term. Now we have to test all those values, but remember when we graphed it and we had those? This is where we got to be smart and use those and try to figure out, do any of those fit our graph? Oops, this keyboard keeps popping up, sorry. And one of them kind of looks close, right? None of those do. None of those are even possibilities. They didn't fit our graph whatsoever. But 3/5, that one kind of looked like, right? That one kind of looked like it's a possibility. It's kind of close there, close to 1, a little bit more than a half. So let's go ahead and test that. So we'll take 3/5 and we'll do synthetic, but we're going to do the synthetic with our new problem there, the 5x cubed minus 8x squared minus 17x plus 12. So we'll plug 3/5 in and test it, see if this works. All right, 5, negative 8, negative 17, and positive 12. Drop the 5 down, multiply that back in, we have a 3. Combine those for negative 5. If we multiply that, it's going to leave us with negative 3. Combined, we have negative 20, and if we multiply those, we have negative 12, which is perfect. That worked awesome. We have no remainder, which means that was an actual solution. And now we can work a little more. So, we've got our 2x plus 1. We now have a new factor. Okay, it's going to be x minus 3/5. Oops, that should be minus. And our new term, 5x squared minus 5x minus 20. And hopefully you guys immediately see that and say, wait. We can factor that. Right. So, Moving on. There's more still. Let's take a GCF out of that new last term. Let's go ahead and rewrite this. 2x plus 1. We've got x minus 3/5 and 5x squared minus 5x minus 20. So we're going to look at that third term. In that third term, we're going to take a GCF out. We could take a 5 out of everything. And we'd be left with x squared minus x minus 4. Right? Still with the other pieces. 2x plus 1, x minus 3/5. And remember that earlier how we took it and multiplied the 2 into it? We're going to do the same thing with the 5. Right? I see a 5 with the denominator. If I multiply it in, it'll kind of give us a nicer term to look at. So we have 2x plus 1. We distribute, we get 5x minus 3. And then x squared minus x minus 4. Now, we're not done, though, because it actually wanted the zeros, right? We have to get this whole thing equal to 0. So, the never-ending problem. 2x plus 1, we already know that. It's going to be x equals -1/2. 5x minus 3, we got that one. It's 3/5. But now we got to focus on the x squared minus x minus 4. We have to set that one equal to 0, and we still have to solve for that. If we do that, we realize pretty quickly this one can't factor. So we need a different method. And that different method, hopefully you remember, it's going to be anytime you have a quadratic, we can always use the quadratic formula. So negative b plus or minus, oops, that's not supposed to be an x, we want the coefficient. -1 plus or minus b squared, which is -1 squared, minus 4 times a, which is 1, times c, -4. All divided by 2a. 2 times 1. Right, let's simplify it. We are left with x equals +1 plus or minus, that's going to give us 17 all over 2. And now we finally have all of our answers. -1/2, 3/5, and 1 plus minus 17 over 2. Write it all out. We get x equals -1/2, +3/5, 1 plus root 17 over 2, and 1 minus root 17 over 2. Incredibly long problem, but you guys won't have too many of those to work with. But that's kind of showing you guys the power of that whole P over Q aspect. We had no clue what those zeros were to start this problem off, but then eventually over time, using P over Q, testing values, and kind of that repeated process over and over and over again, kind of led us to find what those zeros actually were. All right, see you guys in class tomorrow.